Hi everyone. Today we will start in a new topic. The topic is the induction machines. So for this material, we will have some parts, some PDF slides or PowerPoint slides, and I'm gonna share with you the materials of every session as we used to do. So the objectives of the first part of the induction motor material are firstly to understand the construction of the three-phase induction motor. So we said induction machine and now we say induction motor. So what is the difference? We will discuss about that. A second objective is to understand the operation principle of induction motors. Third is to deduce the equivalent circuit. You know that in order to analyze the performance of any machine, we have to have an equivalent circuit and we need to make a mathematical model. So this is one of the objectives here. And lastly here, to learn the power flow in the induction machine. And now we say machine, not motors. So what is the difference when we use the induction machine as a motor or as a generator? So we will discuss all about that in our new topic. So firstly, I have just quick introduction about the induction machine. The induction machine, guys, we consider it as the black horse of the industry because a lot of applications in industry use induction machine. We do prefer to use induction machine compared to DC machine, for instance, because the induction machine has higher efficiency compared to DC motors. And at the same time, it needs just a single supply. You remember that in DC machine, we have two sources, one source for the field winding and another source for the armature winding. The same is also for the synchronous machine. Synchronous machine requires two supply, one for the stator winding and one for the field winding. The field winding is supplied by a DC supply and the armature winding is supplied by AC three-phase supply. However, here in the induction machine, you will find that we need just a single supply, three-phase supply. And you know that for AC machines, we mainly discuss the three-phase machines. Does it mean we don't have single-phase machines? Actually, no, we have single-phase machines. We have single-phase induction motor, and we use this motor in the home appliances. So like washing machines, for instance, like air conditions. So this machine, the single phase induction machine or motor, is used actually in our uh, domestic loads appliances, okay, or domestic load applications. However, the majority of the three phase is in industry. So we will start with the three phase, and if we could finish the topics of our class a little bit early, we can discuss the single phase induction motor as well. So this is an optional topic and we can discuss this point later on. So as we just mentioned, guys, the induction machine needs only a single supply. So from the name, it's induction machine, which means it's self-induction. So self-induction means for any kind of electromechanical machine, guys, you know that in order to convert electrical power to mechanical power, we have to have a source of magnetic field. So in synchronous machine, the field was obtained from the field winding, okay? Or for large synchronous machine, we get it from the exciter. So this is the source of flux. The DC machine also the same. So in DC motor, we have the armature winding on the rotor side and the field winding on the stator side. So we have a source of field. But here in the induction machine, we just have a single source, and the flux is induced or self-induced. And this is one of the advantages and why we use it a lot in industry. On another hand, guys, this type of machine is used from very low power to very high power. So you can use fractional horsepower to tenth or hundredth of horsepower. So fractional horsepower, like for instance, 1/10 horsepower or 1/10 kilowatt or even less than 1/10 kilowatt. So you can find a motor of like 50 watt. Induction motor, 50 watt, like the one, for instance, we use it in fridges, in home appliances, okay? So this is called uh, shaded pole single phase induction motor. Okay, it's very small motor. I will show you some photos for these motors later on. So you can find from very small horsepower to very high horsepower, as you can see, hundreds. So we can find 250 horsepower, 300 horsepower induction motor. So all of that are exist in our uh, in industry. Okay, so this is also another aspect why the induction motor is used a lot in our life. What are the applications we do prefer to use the induction motor with? We have, for instance, pumps, fans, compressors, and these types, we call these types as fan load machine, fan load or fan load types. What is the fan load type? Fan load type where torque is proportional to the square of the speed. So we will draw the torque speed characteristic and see the load and motor characteristic. So for the fan load, all of these types of loads, guys, torque is proportional to the square of the speed. So this is one of the major load types used with induction motors. Besides induction motor, guys, we can find induction generator used in wind energy application. But for the induction generator, we cannot generate electricity by self-induction now because you have to have a source of field. We cannot convert mechanical power to electrical power without this source of field. Okay, so for the induction generator, we would have two different types of machines. One is called self-excited induction generator, and this generator uses some pre-charged capacitors to initiate the flux in the machine windings. And we have another type called doubly fed induction generator. And both are used with wind energy applications. So we have some applications as well for the induction machine as a generator. Now, in order to understand more about the induction machine, let's see the construction. What is the parts of the induction machine? As usual, for any rotating machine, we will have a stationary part and rotating parts. The stationary part, we call it stator. It's typically like the synchronous machine, conventional stator, we have already discussed in the synchronous machine topics. So as you can see here, this is here the core of the induction machine, the stator core. And inside this core, we have slots. And in these slots, we insert our windings. So here, the ends of the windings, as you can see. So these here are the ends of the windings. So you know that we insert the winding inside slot. So we call this one as conductor. And then this goes out and then comes to move in another slot and so on. So this is the way. So inside here we have our conductors, and here we have the ends of the uh, windings or coils. So these are the machine stator windings. And after inserting the machine windings in slots, we do prefer to have some insulators. Okay, so the insulators are covering the windings of the machine, and at the same time, you will find the zip tie that uh, fixing the windings inside the stator. So here is the conventional stator that we used to see in synchronous machine. Again, here, guys, the windings are shifted by 120 degrees or created in slots to have a phase shift, electrical phase shift, or 120 degrees, because this is going to be supplied by three-phase 120 degrees phase shift supply. Okay, so this is the first part, or the first major part in our induction motor. For the rotating part, guys, we have two different shapes. The first shape is called squirrel cage. So the squirrel cage, guys, the rotor consists of laminated ferromagnetic material. If you remember, this was the same construction of the stator core. So the stator core is also made of laminated ferromagnetic material. And for sure, guys, these ferromagnetic materials are insulated just from one side to reduce the cost of insulation, and it has to be insulated to reduce the eddy current loss, like what we discussed before in all of our motors. So this is the shape of the squirrel cage. So here is the laminated ferromagnetic material, and this is here our core. So this is the core that carries the machine winding. So what about the machine winding here? The machine winding here, guys, is gonna be bars, not winding, or not coils, as we used to have in other motors. So this is called cage. This is called cage. If you remember, we discussed about this one in the synchronous machine topic under the name of damper winding. So the damper winding is used in the synchronous machine. And if you remember, we use the damper winding to start the synchronous motor as an induction motor. Today, we will go more in deep and understand the concept of the operation if we have such windings or such a structure in our motor, why this is going to help the motor to start. So again, here is our core, and on the core itself, we will have some holes to insert the machine bars, and then we bought like two rings from both of sides in order to make this cage. Okay, so this is called the squirrel cage rotor of the induction machine. Here is the other shape. So the other shape is still with the same core, but we have external slots. And these slots are used to have the windings like any kind of winding now on the outer slots of the machine. But the induction machine is a three-phase machine, so we have three-phase windings for the rotor. And you know, rotor is a rotating part, is a moving part. So how we will connect the windings while the machine is rotating? So we have here three rings. Every ring is connected to a face, and then we use the brushes connected to the rings to connect these windings to the external world. So we have three-phase slip rings and brushes in the slip ring type. So we call this type, guys, slip ring induction motor or wound rotor induction motor. So this is the second shape. We do prefer, guys, the squirrel cage compared to the wound rotor because you know if you have brushes, this means you need more maintenance for your machine. You have to check the brushes, if the brushes uh, length or thickness uh, reach to a certain limit. So you have to replace these brushes. Otherwise, it may make sparks and cause some short circuits inside the machine if it is not replaced at the proper time. So this is a slip ring induction motor rotor shape. Now, let's see, guys, in order to introduce to the operation, we would like to make like a comparison between the transformer and the induction motor. So you remember that transformer, we have primary winding and secondary winding. For the induction motor, we have also stator winding and rotor winding. So we can represent now our windings typically like the transformer, except that for transformer, we have a single core carrying both the primary and secondary windings. But here in the induction motor, we have two cores because we have air gap between the cores in order to allow the machine to rotate. So this is from the magnetic core's point of view. However, the winding-wise, we can say it's the same as transformer. However, we have a question here. What will happen if the transformer secondary winding is free to move? Free to move means we have another core for the secondary winding, and this core is not fixed. This core is allowed to move. If we supply this transformer, will the secondary side of the transformer move or not? Actually, this is typically now the concept of the induction motor. So, according to the Fleming rules, guys, you know that if you have the magnetic field in this direction and you have a force in this direction, so the induced EMF is going to be produced in that direction. And also on the opposite, so this is for the generating mode. For the motoring mode, if you have the supply and field, so the force will be generated, which means for the transformer, since you already have the field exists already, okay, through the magnetic core, and you supply the electricity from the primary side. So in this case, if the secondary side is free to move, it will move because there will be some forces on the coils. But because the secondary winding of the transformer is wound around the same magnetic core, which means it's not allowed to move, so the secondary winding is not moving. But you have mechanical stress. You have mechanical stress on the windings. For that, guys, the bushings of the transformer have to be checked time to time. It has to be tight enough because the mechanical stress on these screws or pushing terminals of the uh, transformer windings, because of the mechanical force on these windings, this may unscrew the nuts of the transformer. So we have to check these bushings and nuts time to time. So this is a concept now. So by the same concept, we expect that the induction motor is going to rotate because the secondary winding or the rotor winding is free to move. Okay, let's go more in deep to understand the concept. Sorry, guys. So you remember that when we discussed the rotating magnetic field in the synchronous machine, once you supply the machine by three-phase AC shifted by 120 degrees, you will have a rotating magnetic field like what you can see here. So when we supply, this is the stator lamination. This is a stator core after having many laminations together. And inside here, inside the slots, we have the windings and we construct the windings. And this is the final shape. And this will allow when we supply this stator by three-phase AC, so this will allow the machine to have the rotating magnetic field like that. So in this case, how can we make the machine rotating? Simply, can you see here the magnetic field lines are rotating? So this is the rotor bars. This is the rotor structure, and here we have the rotor bars. How these rotor bars will interact and will start moving without having field. Let's see that, guys, more in deep here. So for the beginning, let me draw that here in the beginning. So for the beginning, I'm gonna say I have stator poles at a certain instance, so N and S, and flux is moving from N to S like that. And here we have our rotor. Inside the rotor, I have here two bars. One bar in the upper side and the other bar on the lower side. Now, when the magnetic field, this line N and S, is rotating like that, what will happen to the conductors? So the conductors will see a magnetic field cutting this conductor, which means it will induce an EMF on this conductor. And the same also for the conductor from the other side. But because the direction, guys, this will allow a current to flow like outside of page. Sorry, let's say firstly from the EMF point of view. So if I draw a section or a side view for this file, for this structure. So here is the conductor. This conductor is here, and this conductor is here. Okay, and you got from the moving flux, you got EMF like that here. and you got the opposite EMF from the other side because it's facing the the south pole. So this will have induced voltage like that. So if you have now these conductors connected together, this means you have induced voltage, so you have a source here and a source here, and you have a closed loop that will allow the current to flow. So the current will start flowing like that. If the current starts flowing, guys, it will create its own magnetic field around these conductors. So it will create its own magnetic field around these conductors like that. And then, because you have a magnetic field coming from this director, from the direction from stator, so this is the stator field, it will have a net flux around every conductor. So let's see that here. So for the first, assume this is an S pole. So this means we have north pole on the other side, on the bottom. And here we have the rotor conductors. And the magnetic field of the stator is rotating in this direction. So this is a rotating magnetic field direction. And this is a stator core. Here is the rotor structure. And here the rotor bars. So what will happen is you have the flux lines moving from north to south. So at a certain instant, this is going to be the shape, and this magnetic field is completely rotating, which means it's going to cut the conductor windings. When it cuts the conductor winding, let's see just for one conductor. So there will be an induced volt on this conductor. And because you have short circuit across all conductors, the induced volt will see a closed loop, so a current will start flowing. Once the current starts flowing, guys, it will create flux around the conductor itself. So this is the direction of the flux now around this conductor. Now, let's see the net flux around this conductor. So the main magnetic flux lines are coming from the bottom to the top level like that. From north to south. And here, the rotor field winding is moving in the same direction, which gonna increase the flux in this side of the conductor. Let's see the other side. So stator flux lines are still moving in the same direction, but here the rotor flux lines are moving in the opposite direction, which is going to reduce the flux in this direction. So you have here a lot of flux lines, few flux lines, so this will create a force to move this winding toward this direction. This is going to move this conductor towards this direction. And because in this configuration here, so if this conductor is going to move in this direction, and the other conductor, since it's in the other side to the other pole, so they're going to move in the opposite direction. So this is going to create now, so this is a force, this is a force, and you have here a distance between the two conductors. So this is going to create a torque. And this torque will rotate this body. So this means, guys, we don't need a source of flux. The induction motor itself could start rotation without external source of flux. Just to supply the field, sorry, the armature or the stator windings by three phase. This is gonna make the self-induction and rotate the machine. And as you can see here, guys, this is here the shape of the rotating rotor and the direction of the current, and even here with the induced voltage magnitude increasing and decreasing according to the direction of the flux. So this is the concept and the operation of the induction motor. So we can say now, guys, the rotating flux produced by stator winding cuts the rotor winding. This is the first stage. Second stage is, due to the short rotor windings, a current will flow in the rotor windings and produce its own flux. Produce its own flux, or I like the expression, and make or induce self-induced flux. We don't have an external source for the flux. Then the net flux from the stator and rotor sides, stator flux and rotor conductor flux, the net flux forces, or the net flux makes force on one conductor and torque on one turn. So one conductor will see a force, and the complete turn, the two conductors together will see a torque, causing the motor to motion. So this is, guys, the summary for the operation, how the induction motor starts rotating. A question here, guys. What is the flux cutting speed when the rotor speed equals the synchronous speed? So this is very good question. Firstly, what is the speed of the rotating flux? You know that the speed of the rotating flux is nothing but ns. So since the supply is or has frequency f, so we expect that the synchronous speed to be 120 times f divided number of poles of the machine. So this is the synchronous speed and the same speed of the flux coming from the stator side. But can you imagine now here for this conductor, guys, if this conductor is already rotating with the same speed of the field, is there any kind of cutting between the magnetic flux lines and the conductor itself? So if both are rotating with the same speed, there will be zero cutting speed. So the cutting speed now is the difference between the flux, stator flux and rotor flux. Stator flux and the rotor field around the conductor itself, correct? Or let's say the cutting speed is the difference between the flux of the stator and the motion of the rotor. So if the rotor is rotating with the same speed now, the cutting speed will be zero, which means zero induced voltage will appear. So this means, guys, the induction is gonna stop. The machine is gonna stop because the generated volt became zero. So what will happen is, in the beginning, the machine will start motion with a speed called nr. And this nr should be less than ns. However, if nr increases to reach to the same synchronous speed, what will happen is the cutting speed will be zero. The cutting speed will be zero. And again, cutting speed means ns minus nr. If a cutting speed reaches zero, so this means the induced voltage will be zero. If the induced voltage became zero, so this means no current will flow on the rotor bars or rotor windings, which means also that the machine will start slowing down. It's not gonna be stopped completely at zero time, because you know that mechanical time constant, guys, is much larger than electrical time constant. So the machine will start slowing down because the source of torque became zero. The source of torque, which is your current. So the machine will start slowing down. But once you slow down the machine, this means cutting speed is not zero anymore. So you will have a cutting speed, and this cutting speed will produce induced volt and then will produce current. And this is going to speed up the machine again until getting the same synchronous speed. So it's like a rotating cycle, guys. It's endless. What will happen is the machine speed is going to be now rotate with a speed between two limits. The maximum limit is ns, and the lower limit is another speed less than ns by very small interval. And we are going to call the average speed as nr. So I can say that the machine speed is rotating like that now between this slip and ns, or this limit and ns. In order to get a fixed number, so we will call the average speed as a function of something between the band we have here, which is going to call slip. And physically, this slip, guys, is 1/2 of the distance or the limit between ns and this speed. And the average speed here is called nr, which is the rotor speed. So this is a concept now. So in this case, guys, we need to define the slip term. So the slip is ns minus n, which is the rotor speed, and let's say nr or n. But let's make it in percent or in per unit of the synchronous speed, so we will divide over ns. So this is going to be the slip in per unit. Okay, so this is a per unit slip of the machine. So defining the speeds again, we have now N2. So we will refer to the rotor side, guys, by R or 2, like transformer, secondary side or 2. So 2 here is referring to the rotor side. So N2, the speed of cutting, so the cutting speed to rotor, equals ns minus n, which is the rotor speed. So we can say that ns minus n equals slip times ns, because we just said s equals ns minus n divide ns, and n is the rotor speed. So this is called, guys, the cutting speed. And the cutting speed is the difference between the synchronous speed and the rotor speed. So let's delete it. Hence, the rotor current frequency equals F2, because the current that will be generated on the rotor winding now will have the same frequency of the speed. So we will call it F2, which is related to the speed N2. The speed is, the rotor speed is N, and the stator current and the flux frequency is F1, which is the frequency of the synchronous speed. So these are the different frequencies and speeds we have now. So we have 3 different speeds, guys. The synchronous speed, which is the stator current speed or flux speed, the rotor speed, the rotor current speed. Sorry, this is synchronous. The rotor current speed. So this is rotor current speed. And speed, guys, because we relate the current also to the frequency. So speed and frequency, we can say it's in period the same thing. So this is called now the rotor current, not rotor speed, rotor current speed, rotor current speed, or rotor current frequency F2. This is called N rotor speed. Okay, and ns is the synchronous speed or the stator current speed or the flux speed. Okay, so these are the three speeds that we have right now, and this is the definition of every speed. So again, the synchronous speed depends on f1, which is the supply frequency. The rotor speed, which means the mechanical motion speed of the rotor itself, this depends on the difference between stator frequency and rotor frequency, F1 minus F2, and this is the mechanical motion speed of the rotor itself, and the cutting speed N2, which depends on the slip and frequency of the rotor current, which is F2. So these are the three speeds we have in the induction machine. Now, guys, if we say now F2 as a function of the speed is going to be P divided 120, P is the number of poles, times Ns minus N. So this is now the cutting speed, N2. So we can say, guys, it's P divided 120 times slip times Ns. And if you see here, Ns times P divided 120, it's nothing but F1, which is the supply speed. So we can say by the end, F2 rotor current frequency equals S slip times F1. So this is the relation between the two frequencies. And we mentioned, guys, that S is very small number. So S can be like 0.01, 0.02, very small number. So this leads to having very small frequency for the rotor current. So the rotor current frequency is very close to the DC. You know, DC frequency is 0. So you can find that the rotor current frequency is 1 hertz, 2 hertz, something like that. Very small frequency compared to the supply frequency. What about the induced volt? You know that any EMF, guys, equal 4.4 times frequency times number of turns times peak flux times winding factor. So this is the relation of the EMF. So in this case, the induced volt at the rotor winding is going to be depending on F2, which is S times F1. So we can relate the E2S, E2 cutting during motion, E2, or the induced volt during motion equals S times E2, which is the induced volt during standstill. It's like transformer, guys. Okay, so this is the relation between the induced volt during motion and standstill. So this is the relation for the induced volt. Why we drive these relations? Because we need to find now an equivalent circuit for the induction motor. So we will drive the equivalent circuit of the induction motor from these terms right now. Also, regarding the cutting speed itself, we can say N2 equals 120 F2 divide number of poles. So replace F2 by the value you have here, SF1. So this ends to N2, which is the cutting speed equals slip times Ns. So these are the different relations we will need. Before of driving the equivalent circuit, guys, let's solve a quick numerical example about the speeds we have in the synchronous machine right now. The example says, guys, a three-phase 460 volt, 100 horsepower, 60 hertz, 4 poles induction machine delivers rated output power at a slip of 0.05. So this is S equals 0.05. And we need to determine the following. Firstly, find the synchronous speed and motor speed. Synchronous speed means ns. So we can say ns equals 120 times frequency of the supply f1 divide number of poles. So frequency of the supply is 60 hertz times 120 divide number of poles is 4. So 120 times 60 divide 4. So this is going to be 1800 RPM. And the motor speed, so you know that N equals 1 minus S times NS. So this is 1 minus slip equals 0.05 times 1800. So if you calculate that, the value is going to be 1710. So 1710 RPM. Now, the speed of the rotating air gap field. You know that any air gap field, guys, is going to be the same as ns. So this is 1800 RPM. Frequency of the rotor circuit. Frequency of rotor circuit means the frequency of the current flowing in the rotor circuit, which is F2. So F2 equals S times F1. So this is going to be 0.05 times 60 hertz. So this is 3 hertz. Slip in RPM. So this is slip in RPM means S times NS. So this is going to be now 0.05 times 1800, which is 90 RPM. And for sure, this is a difference between NS and N. Then this question is very interesting, guys. The speed of the rotor field relative to. Firstly, what is the speed of the rotor field? Now the rotor field has a speed around the conductor, and the rotor itself is moving with the machine speed. The summation of both speeds will make the machine flux. All the machine flux is going to move with the synchronous speed. So any speed, any flux speed, guys, we have in the machine will be the same as the synchronous speed. Okay? Whatever rotor field or stator field, so every one is going to be, or total speed of any flux is going to be the synchronous speed. How it comes? The rotor field should be a function of the frequency F2. This is correct, but this is around the conductor. And the conductor itself is rotating with the speed of rotor. So now you have two speeds in order to relate a speed to a stationary part. So if you would like to measure any speed, you have to measure that speed relative to a stationary part. So for that, guys, all the machine flux will be rotating with the synchronous speed. So now this question says, what is the speed of rotor field relative to? Relative to means we need to subtract the ns from any of these speeds to find the relative speed. Firstly, relative to the rotor structure. So rotor structure is going to rotate with n. So in this case, the field speed is going to be ns minus n, field relative speed to the rotor structure, which is going to be now 90 RPM. Compared to the stator structure, the stator structure, stator is fixed structure. It's not going to move. So this means ns minus 0. So this is going to be the 1800 RPM. Compared to the stator rotating field of the stator is ns. So this means ns minus ns. So this is going to be 0. Okay, so this is called, guys, the relative speeds. And here is the answer of all the parts we already solved. A last question here is, what if the rotor induced voltage at the operating speed if the stator to rotor turns ratio is 1 to 0.5? So this is the turns ratio in stator to in rotor. This is not speed, this is number of windings. So you can say N stator divide N rotor equals 1 divide 0.5, which is 2. So this is the turns ratio of our induction motor windings. So the question here, find the induced volt at the operating speed, which means at the rotor speed, if the stator to rotor turns ratio is this ratio. How can we solve this question? So we just drive the relation together. So the induced volt on the stator winding at motion equals S times E2. S times E2. So E2 is the induced volt on the secondary side, on the rotor side. How can you get that from E1? Use the Turner's ratio. So N2 divide N1 times E1. So this is now the value. So S is 0.05. The N2 divide N1. So this is the opposite, which is 0.5 right now, time the voltage of E1, which is the supply volt. But the supply volt is given line to line. So per phase, we would divide over square root of 3. So 460 divide root 3. So this is going to be the induced volt that we need. Okay. Nice. Okay, so this guy is the example here just to let you know the concept of the different speeds we have in our machine. Okay. Nice. For the equivalent circuits, I'm going to start this right now and we will continue in the next session. So this is the stator circuit. So stator circuit is, you know that we have windings, so you will have resistance for these windings. You would have leakage reactance for these windings. And here we have the core parameters. And this is the induced volt on the stator side. So this is E1. And take care that X1 is a function of the frequency F1, the stator supply frequency. And the same is also for the core reactance or equivalent reactance of our core magnetization reactance. So this here represents the stator winding at standstill. Standstill means the machine is not moving yet. And this is the definition of all of these parameters. As you can see, guys, it's typically like the stator of, sorry, typically like the primary winding of the transformer. And here, guys, this is per phase equivalent circuit of the stator, because you know that we have 3 phases. When the stator, when the machine starts moving, what about the rotor now? So firstly, rotor circuit, you will have the inductance and resistance. So resistance is the rotor winding resistance. And you have here the leakage reactance of your rotor. And you know that X is the reactance itself, but due to motion, we would multiply that times S. Why? Because you know that if we relate to the frequency, so X2 should be 2 pi F2 times L2. And F2 is S times F1. So we can say it's equals to here we can say it's S times 2 pi F1 L2. So we are going to consider that all reactances are a function of frequency F1. So we would multiply here times S. And the same is also for the induced volt during motion. I'd like to get the current relation, guys. So I can say for the current relation from the first figure here, so I2 is the volt, which is SE2, divide the impedance of the circuit, which is R2 plus SX2, but don't forget the J because this is impedance. If you divide numerator and denominator over the value of S, so this would be E2 divide R2 divide, sorry, R2 divide S plus JX2. So this relation, we can say that we have induced voltage source. This is the induced voltage source. Reactance X2. This is the reactance X2. And a variable resistance R2 divide S. So this is the R2 divide S. So we just modified the shape of the equivalent circuit, but still, this is volt. This is the same current. But we made the circuit as a function of the slip, the resistance as a function of the slip. If we divide R2 divide S to these two parts, is it gonna change anything? Let's see that, guys. So if we have these two elements series together, so R2 prime, or sorry, R2 plus R2 divide S times 1 minus S. So this means, or this equals R2 plus R2 divide S minus R2 times S divide S, which is R2. So this will lead to the same term R2 divide S. So we can say R2 divide S equals two series resistances. The physical resistance of the machine, which is R2, the physical resistance of the rotor windings, and another resistance comes because of the operation. So this resistance, guys, is not a physical resistance, but this is just came due to the operation of the machine. Because if the machine is at standstill, the machine is not working. So this means S equals 1. So the relation of S again, S equals NS minus N divide NS. So if N is 0, so this means S equals NS divide NS, which is unity. So if the machine is at standstill, S equals 1. If you substitute here at S equals 1, so this leads to that this term is going to be 0. So this is not a physical resistance, but this is just a term comes because of the operation of the machine. So this is now the rotor equivalent circuit. If we mix the two circuits together now, let me clean this part now. So if we collect the two circuits now, the stator circuit and the rotor circuit together, we will end up with that equivalent circuit. Okay. Next session, guys, we will start from this point and continue discussing the equivalent circuit of our machine. Thank you so much.